One of the rules that we're adding to our proof system is the universal elimination rule. The universal elimination rule gives you a way to argue from a universally quantified whiff. And by a universally quantified whiff, we mean any whiff that starts with a universal quantifier, such as for all x px, everyone likes pizza. For all x, if tx, then fxj, everyone who's a toddler is friends with James. Or for all x, there is a y such that nxy, everyone has a neighbor. And what the universal elimination rule says about how you're allowed to argue from these types of statements is incredibly simple. It says that given a universally quantified whiff, you can derive any instance of it. In other words, it says that if you know that everything in the domain has a certain feature or characteristic, then you can take any individual thing from the domain and conclude that it has the feature in question. For example, if you have for all x px, everyone likes pizza, then you can conclude PA, Alex likes pizza. You can conclude PB, Bob likes pizza. You can conclude PJ, James likes pizza. You can conclude PN, Naveen likes pizza, and so on and so forth. If you have for all x, there is a y such that nxy, everyone has a neighbor, then you can conclude that there is a y such that nay, Alex has a neighbor. You can conclude that there is a y such that njy, James has a neighbor. You can conclude there is a y such that ny, Naveen has a neighbor, and so on and so forth. Because whatever can be said of everything can be said of each individual thing separately. The universal elimination rule is really as simple as that. Now, just a couple of notes. First, you can use the universal elimination rule multiple times on the same universally quantified whiff to derive multiple instances of it if you want. For example, suppose we're given the premise for all x fx, meaning this time everyone's funny. And the conclusion we're supposed to derive is fn and fm, both Naveen and Magnolia are funny. Then we just use the universal elimination rule a first time to derive fn, and then a second time to derive fm, and then conjoin those two. Second, the one mistake that people tend to make with the universal elimination rule is applying it to formulas that are not actually universally quantified whiffs. For example, they'll have a premise like not for all x fx, and they'll appeal to universal elimination to derive not fa. But that's a mistake because not for all x fx is not a universally quantified whiff. It's the negation of a universally quantified whiff. So the universal elimination rule can't be applied to it. And it would be invalid reasoning to derive not fa from not for all x fx. Because what not for all x fx says is that not everyone is funny. Given that premise, you can't then take some arbitrary member of the domain and conclude that they must fail to be funny. You don't know that. All you know is that at least some people in the domain aren't funny. An arbitrary person you select might be one of those unfunny people, but they might not be. So from not for all x fx, you're not entitled to conclude not fa, and the universal elimination rule doesn't allow you to do that. If you had for all x not fx, everyone is such that they fail to be funny, then you could use universal elimination to conclude not fa. Similarly, for all x fx or for all x gx, and if for all x fx, then for all x gx are not universally quantified whiffs either. The first is a disjunction, which happens to be a disjunction of two universally quantified whiffs, and the second is a conditional, which happens to have a universally quantified whiff as antecedent and another universally quantified whiff as consequent, but neither are themselves universally quantified whiffs, and so the universal elimination rule can't be applied to them. So you can't derive FA or GA from the first, for example, and you can't derive if FA then GA from the second. By contrast, for all x, fx or gx, and for all x, if fx then gx are universally quantified whiffs, and so you can apply the universal elimination rule to them. FA or GA can be derived from the first, and if FA then GA can be derived from the second.